This is the second part of lecture 5. We will continue on solving the support vector machine. And in the previous part, we talked about hard margin SVM, where everything needs to be classified correctly. And we saw that this is kind of difficult to solve. So we want to simplify it while allowing some mistakes. So let's draw a diagram. And we have, say, arts here, and we have trash cans here. And these are arts, these are trash cans. And suppose we have like one trash can that looks really nice, let's say here, and maybe we have an art that's really garbage. So we still want this line like this, but if we actually use the formulation here, none of the W's will be able to satisfy this condition. So there will be no solution basically to the constraint optimization problem. And what we're going to do is we are going to, again, allow mistakes, and we're going to call the mistake the slack variable. So we're going to call the distance here that's the way I'm writing psi, so it's the Greek letter xi, but my handwriting is not great. You will see the typed version in the next slide. So let's suppose this is our x1, then our xi1 is basically the distance between this point and the line, and also suppose this is our x2, then this length would be our xi2. And for the other points that are classified correctly, we do not have negative xi values. Say this is x3, we will just let it be equal to 3. So basically this variable just represents the amount of mistake. If there are no mistakes, the mistake is 0, it's not negative. And we are going to call this the soft margin SVM, and we are going to have a cost of having a mistake, and the cost is constant at, say, 1 over lambda. And so the problem can be written like this. So we are going to minimize like something like 1 over the margin, and there are actually squares and constants, but let's just say 1 over the margin. And also there is an additional cost from mistakes. And this is actually the average mistake, or the average incorrect distance from the line. And we're going to have the same constraint, but we are going to add the mistake into the constraint. So we are actually allowing those mistakes to happen. If we don't have this, then it's the same problem as before. There will be no solution. And we require these to be larger than or equal to 0. So this is the way that I should be writing psi. So I am also pronouncing as this, as psi, and I know some other people pronounce it as xi or whatever, but I'm just going to say it this way. So in any case, I copy the same expression again, and we need to simplify this. So here, the first thing we need to do is we need to rearrange this so that it looks like our psi I is it larger than or equal to 1 minus 2yi minus 1 w transpose x plus b. That will be the first step. And the second step is, notice we want to minimize this. So the mistake is kind of as small as possible is good. So this needs to be as small as possible. So in particular, if this can be 0, we just need to make it 0. And if it's positive, we just set it equal to basically the minimum amount of mistake. And that leads to just setting psi I equals to the maximum of the two. So if you want to see this purely mathematically, the constraints are this variable is larger than one thing and this variable is larger than another thing. So you want the smallest psi I that's larger than both of these. So what number should you use? Of course, you are going to use the maximum of these two. So whichever is larger, we're just going to use that. And that will be a number that's, say, as small as possible when we put it back into the sum. So basically, using this logic, we can say that psi I is equal to the maximum of these two. And when things are equal, when we have an equality constraint, we can just substitute the constraint back into the objective, and we will have an expression like this. This is the expression that we want. And that looks complicated, but that's just one expression. We can take the derivative and just use gradient descent again. So there's one problem, the max function is not differentiable. So we should figure that out. So here, if you look at this expression, it looks like it's almost differentiable, but there's at one point, at this point when they're equal, it's not clear how to differentiate that. So to give you a simple example, suppose you have max 0 and x, let's say y is that, then if you draw that, it becomes, this is our x, this is our y. When you draw it, it's this. So the slope in this region, slope in this region is 0. The slope in this region is 1. We don't know what's happening at here because there can be multiple slopes like this one, or there can be many of them. And we are just going to say we use any one of these. And we're going to, again, give it a fancy name. And these things, like these slope-like things, they are called subgradient. I mean, in one dimension, it's called subderivative, and in higher dimensions, it's called subgradient. So basically, given a convex function, it's the set of slopes of lines that are tangent. So there is a very mathematical definition. You don't need to know this at all. It's just, if you are interested, the subgradient is defined as basically the set of possible gradients at a point. And we're going to use this partial derivative notation again. So I'm going to pronounce it as df, and it's not really a partial derivative, but we're using the same notation. And now we can differentiate this. And what we're doing is basically assuming at this point the slope is 0. So that's basically it. And it has a fancy name, and that's it. And we are going to just use this expression as the derivative. So when the thing inside the max is above 1, we're going to use 1 as the slope, and otherwise we're going to use 0, including this point here. And know that this subgradient becomes a set. So the notation here basically is the opposite of this. This is an element of. So is an element of. So basically this is one possible subgradient among the many possible subgradients you want to have. So basically we're just going to use something simple. And same thing for the derivative with respect to the bias. And we are actually not going to use the bias, so I'm not going to spend time talking about this. And there is one thing that I do want to talk about is in practice, let's say, or when people actually try to solve this, we usually do not include the bias term, so we only have the weights, and we are going to label stuff as -1 and +1 at the beginning. So we used to do things from 0 to 1, but when we're talking about spot vector machines, we usually just use this 2y + 1 thing, either +1 or -1 as our label. So that would be one choice. Then the gradient descent step can be written very neatly like this. And if you actually look at it, it looks like the activation. So remember, we have this yi minus ai thing times xi and have a sum for the perceptron and the logistic regression, right? So this looks like basically the same. And we have this x at the end as well. So one thing that's extra, so if you go back here, you have this minus lambda, so I put this outside. And remember when we talk about regularization in the previous lecture, so if you think about L2 regularization, you are adding basically the norm of W, which is just basically the W transpose W, and when you differentiate this, it becomes just W. And if you have a parameter, if you have a regularization parameter in front, you are subtracting lambda W every time, which is exactly what this is doing here. Right? So the W here looks like it's a regularization parameter. So that's why it is called a regularization parameter. It's not actually regularizing anything. So it just turns out you have an expression with a lambda we're subtracting lambda every time. So it looks like it's regularizing already, and it's called the regularization parameter. And that's it. So of course, for all of these algorithms, we need to give them like super fancy names. And the stochastic version of the subgradient descent that we just talked about is usually called Pegasus, and it's primal estimated subgradient. A is capitalized, solver SO are capitalized, and S for subpart vector machine. So in the next slide, I just summarized what we had. Is one thing to notice is first, this y needs to be converted to z, and you also need to randomly permute because we are doing stochastic gradient descent. So shuffle the training set and basically perform the gradient descent step for each instance. And instead of waiting for it to converge, it's usually done for a fixed large number of iterations.